Welcome back. In the previous video, we discussed arc length with respect to x, integrating with respect to the x variable. But we can't do that if the function is not continuous at some point on the curve. There's a discontinuity or that it's not differentiable. It is possible, however, that instead of dealing with the derivative of y with respect to x, that if we look at the derivative of x with respect to y, all right, that one could exist, that could work. Sometimes this happens, and this is important, when we have a vertical tangent line. Okay, so if we start with an equation, y in terms of x, we can rewrite that equation as x in terms of y in many situations. Here we have a formula for the length of x as a function of y. So as long as x is some g of y, as long as the derivative is continuous on the closed interval, the length of the curve from 2 points A and B, defined as my interval C and D, then we work it the same way. You'll just notice my bounds are C to D, and instead of dy dx, I have dx dy squared, integrating with respect to y. And like I said, this occurs, or we need to use this method when we possibly have a vertical tangent line somewhere on that closed interval. So we may need to take our function and rearrange it, or it could be presented that way as well, but we may need to take y equals x and turn it into x equals some function of y. All right, and then we can differentiate and use our formula the exact same way. It's pretty simple. You just need to notice or recognize when you should integrate with respect to y instead. So let's do an example. Here, we're going to find the length of the curve y equals x over 2 to the 2/3 power from x equals 0 to x equals 2. And if we are to graph this on our calculator or whatever our graphing mechanism is, we get something that looks like this, symmetric. And of course, we don't care what's happening over here on the left side of my y-axis. So we're really just concerned about what's happening between 0 and 2. But again, considering that graph, what continued over here, if I were to try and determine what the tangent line to the function would be right here at 0, it would be vertical, right? So it's not differentiable at x equals 0 because there would be a vertical tangent line there. And vertical line is not a function. So in this situation, we would recognize that we're going to take this function and rearrange it. And then it's pretty basic for us to solve. And even if I didn't graph it, if I took that function and I went to go take the derivative of x over 2 to the 2/3, well, the derivative of y with respect to x would be 2/3 x over 2. 2/3 take away 1 is negative 1/3, and then we would have that, would take the derivative of the inside, would give us not an equals there, we would have times 1/2. And if we look at simplifying this, those 2's would cancel and this negative power would flip that fraction. dy dx equals 1/3, 2 over x to the positive 1/3. And you'd notice right here, this is not differentiable. I can't plug 0 into the function, right? This is a problem. We're not defined at x equals 0. So there's also a clue why we might need to rearrange our function so that we can solve for the arc length here. So let me get rid of all this. We're going to take our function y equals x over 2 to the 2/3, and I'm going to rearrange it so that instead of y equals x, we'll have x in terms of y. So that would be y equals 3/2. Y to the 3/2 equals x over 2 multiplied by 2. 2y to the 3/2 equals x. So the derivative of x with respect to y, that would be 2. We would have 3/2 y, take away 1 from that, to the 1/2. Or dx dy equals 3 square root of y, or y to the 1/2. So just to recap, I have my function x in terms of y, and I took the derivative of x with respect to y, which gave me this. So remember, we need that derivative squared. So dx dy quantity squared is the same as 3y to the 1/2 squared, or 9y. So this is going to look very similar, the integration here, to what we did in the previous video. All right? We just had to take some extra steps at the beginning to rearrange our function because it would not be differentiable at one of those endpoints of the closed interval. So, working through this, my arc length formula, L, is the integral from C to D. Those bounds, I'll put them up there in a second. We're going to go look at that. And then we have the square root of 1 plus dx dy squared, which is 9y, and that's going to be integrated with respect to y. All right, so what are my bounds? You might be inclined to come over here and use this 0 and 2. But since it's in terms of y, we need to say, well, what are these values here? What's this point and this point? And so this is from 0 to 1. So I'm going to come down here and plug my 0 and 1 in. All right, so this becomes the integral from 0 to 1. I'll rewrite that as a 1/2 power. And we're going to use a u substitution. So u equals 1 plus 9y. So the derivative of u with respect to y is going to be 9, or rather 1/9 du equals dy. And then we'll look at changing those bounds. If u equals 1 plus 9 times 1, that's going to give me 10. And if u equals 1 plus 9 times 0, that's going to give me 1. So this becomes the integral from 0 to 1 of u to the 1/2, and then we have times 1/9 dy. And I'd like you to notice what I did there. Our bounds should have changed. I went ahead and rewrote them, but that should be from 1 to 10. Right? So don't forget to do that. Remember, if I left them in terms of y, then I would have to plug this 1 plus 9y back in at the end. But I don't want to do that. So it's much easier for me to just say, hey, let's change them. And I recommend you always stop, take a look, make sure you've set that up correctly. So now this is pretty easy for us to integrate. The 1/9 is going to come in front. U to the 1/2. You add 1 to the 1/2, you get 3/2. So this is 2/3 u to the 3/2, and we'll need to evaluate from 10 to 1. So pulling that 2/3 out, I have 2 over 27. U to the 3/2, I've got 10 to the 3/2 minus 1 to the 3/2. And I really can't simplify this much more. 10 to the 3/2 is the square root of 10 cubed, or the square root of 1,000. So just simplifying that one term, I would have 10 root 10 minus 1. And this represents the exact length of my curve between x equals 0 and 2, or y equals 0 and 1. As always, email me if you have any questions.